So I hope you got some good experience there in actually applying what you learned to create a neural network that can classify masses found in mammograms as benign or malignant. Like I said, I got around 80% accuracy myself. I wonder how you did. Anyway, I started off by just blindly reading in the CSV file using pd.readcsv and taking a look at it. And I saw at that point that the column names were wrong. There was missing column name information in the data file. And there were missing values in there that were indicated by question marks. So have to read that in a little bit more intelligently. So on my second try here, I called read CSV, passing in explicitly the knowledge that question marks mean missing values, or NA values, and I passed in an array of column names like we did before, and did another head on the resulting pandas data frame, and things look a lot better now. At that point, we have to clean the data now that it's in a proper format and organized properly. We can do a describe on that to take a look at things and get an idea that we are missing some data, and things seem to be reasonably well distributed at least. At this point, we did a little count here to see what exactly is missing. So my strategy here was to see if there's any sort of bias that I'm going to introduce by actually removing missing values. And if I were to see that the missing data seems to be randomly distributed, just by eyeballing it at least, that's probably a good indication that it's safe to just go ahead and drop those missing rows. So given that I've determined that that is an okay thing to do, I've gone ahead and called drop NA on that data frame and described it. And now I can see that I do have the same number of counts of rows in each individual column. So I now have a complete data set where I've thrown out rows that are missing data. And I've convinced myself that's an okay thing to do statistically. All right, so now we need to actually extract the features and values that we want to feed into our model, our neural network. So I've extracted the feature data, the age, shape, margin, and density, from that data frame and extracted that into a NumPy array called all features. I've also extracted the severity column and converted that to an all classes array that I can pass in as my label data. And I've also created a handy dandy array of column names since I'll need that later on. So just to visualize, I've punched in all features just to take a look at what that looks like. And sure enough, looks legitimate. Looks like an array of 4 features apiece on each row. Looks reasonable. At that point, I need to scale my data down. So to do that, all I need to do is import the preprocessing.standardScaler function there and apply that to my feature data. And if I look at all features scaled that came out of that transformation, I can see that everything appears to be normally distributed now, centered around 0 and with a standard deviation of 1, which is what we want. Remember, when you're putting inputs into a neural network, it's important that your data is normalized before you put it in. Now we get to the actual meat of the thing, actually setting up our MLP model, and I'm going to wrap this in such a way that I can use scikit-learn's cross-val score to evaluate its performance. So in my example here, I've created a little function called createModel that creates a sequential model, adds in a dense layer with 6 units or 6 neurons using the ReLU activation function. I've added in another layer with 1 that does my final sigmoid classification, my binary classification on top of that, and I've compiled that with the Atom optimizer and the binary cross-entropy loss function. So with this, we've set up a single layer of 6 neurons that feeds into one final binary classification layer. Very simple. And I've then gone ahead and used the Keras classifier to build a scikit-learn compatible version of this neural network, and I've passed that into cross-val score to actually do k-fold cross-validation, in this case with 10 folds, and print out the results. So with just these 6 neurons, I was able to achieve an 80% accuracy in correctly predicting whether or not a mass was benign or malignant just based on the measurements of that mass. Now, in the real world, doctors use a lot more information than just those measurements, so our algorithm is kind of at a disadvantage compared to those human doctors to begin with, but that's not too bad. If you did better, if you used more layers, more neurons, I'd be curious to see if you actually got a better result. It turns out that sometimes you don't need a whole lot to actually get the optimal result from the data that you have. But if you were able to substantially improve upon that result, congratulations. So I hope deep learning has been demystified for you. And up next, we'll talk about how to continue learning more in the field of deep learning.